Hello, welcome to this YouTube channel. Today I'll be showing you how you can carry out a molecular docking of metal complexes using the molecular operating environment as well as Gaussian and Mercury. Now in this tutorial we'll be using structures that have been downloaded from a database. Now, we have databases such as PubChem, CCDC, COD, and we'll be using the structures we've downloaded from these certified chemical databases. Now, this is quite different from the last tutorial. In the last tutorial, we actually designed the complex, we modeled the complex from scratch and then we eventually use it for molecular docking. But in this case, we will be downloading the structures from a database and then we'll carry out molecular docking of that structure. Now, the first thing to do in this in carrying out molecular docking of metal complexes for this kind of work is to download the structure. Now, we'll be downloading our structure from CCDC. So you download your structure. After you've downloaded your structure, that is the structure of the metal complex. The next thing is to optimize the geometry of that metal complex structure. Now, the advantage of downloading the structure is that for many of these databases, every structure you find has been experimentally verified. So you are working with very reliable structure. And then when you have to optimize, you will not optimize using DFT again. When we design a structure or model a structure from scratch, then we have to use DFT to get a very reliable result. But for structures we've downloaded from verified database, you don't need to use DFT. Instead, we can use molecular mechanics or simply semi-empirical methods to actually optimize the geometry of the metal complex. Now, this is very advantageous because you will be spending less time and less computational power. If you've tried to carry out DFT of metal complexes, you observe that it takes a lot of time, hours, and for some people, it takes days. But with this will just take minutes and then you're done with your optimization. The next thing to do is to prepare your protein and then carry out molecular docking. When you're done docking, you're expected to analyze your result and visualize the interactions responsible for the docking scores you obtain. Now, let's go to the practical session. Now, we'll be considering the antidiabetic potential of a copper complex. Now, the structure of this complex is shown here, and this complex, the CDCC number of the complex is 1030214. So, what we're expected to do is to use this number to obtain that structure, and then I will show you what to do next. Now, this is the protein target we'll be using. So let's get to work. Now, the first thing I'll be doing is to go to now CCDC. Now, this is ccdc.cam.ac.uk. So that is where you're expected to go to. So click on Access Structures. Okay, cool. So that's good. Now, the next thing we want to do, let me go back to and then let me copy that number. So what you're expected to do is to go through literature and then if you have papers that have carried out X-ray verification of complexes, they will drop the CCDC number there. So you can actually use that to obtain your structure. So once I put it here, I can search. Okay, wow, this is good. Now, so you can see the structure of the complex you'd be working with. So what we are expected to do is to download the current entry. So click on download and click on download current entry. Now you can see that. So now it will require that you put your email, your name and your institution if you wish, but your email must be there. So what I need to do is just to download. Now it will get downloaded. Now another thing I think I want you to note is you can also use the citation of the paper to actually get the CCDC. So a lot of times there are a lot of things you can do to actually get the CCDC number. Also, I will navigate to that. So let's click on it. Now you can see that it downloaded a CIF file. Look at it. This is a CIF file. So please, when downloading, make sure you are downloading a CIF file. So I want to copy this and I want to place it in this complex. I mean in this directory. I would like in this folder. So I would like to work with all of everything I have. I would like it to be in one folder. Now, once you've done that, the next thing is to open Mercury. Now, Mercury is a very important software that you use to assess crystal structures. If you want to open crystal structures, a lot of times you would have to use Mercury, and then it's free, so you can easily download it if you're an academic, and then use it for whatever you want to use. But if you want to use it for commercial purposes, then you might have to pay for a license. So open Mercury. Good. Now go to File, go to Open, and then navigate. We want to navigate to Downloads. Okay, docking, and then open the CIF file. So click on it. Oh, this is it. Now look at the structure now. Compare this structure with the structure you have here. So this is a copper complex. You have water, you have NH2, that's ammonia, coordinating to the copper. So let's go to this so you can see this now. But if you look at this structure, you observe that the aromatic rings are not represented as aromatic rings, so we'll have to adjust that. You can also choose to look at some of the contacts. You can also see hydrogen bond interactions just with respect to that complex. Now, if you want to see the label of the atoms, you can see that. So you can see copper bonded to different ligands. You can see that. But we are not interested in that. You can also look at the axis. Now, if you try to use it like this, then you would have issues. You will discover that your structure is not representative of what you are working with. So we would have to adjust the structure. So go to Edit and go to Edit Structure. Normally, it should have recognized the aromatic rings, but I don't think it did. So we will simply um, make it do that. So go to click on auto edit, and then we want it to guess bond types for only bonds with unknown types, and we want it to detect aromatic bonds and to also add missing hydrogen atoms. So click on apply. Okay, you can see that. So accept. Now, so you can see that the structure looks very presentable. It looks correct because we now have the aromatic rings that we expected. Look at this. We had aromatic rings, so you can see that. So let's go back there. Now, what do we need to do then? We have to save this file as a MOE2 file. The advantage of using Mercury is that Mercury is very good at exporting MOL2 files for crystal structures, especially if you've downloaded it from CCDC or a crystallographic database. So I'll go to Save As. If you use other softwares, you have a lot of challenge doing that. So we want to save it as a MOL2 file. So what do I call this file? I will call it let's look at the code name 10302114. So I'll call it one, let's call it copper, and then 103 130214. Okay, 214. .mol2. So this is fine. So I'll save it here as a mol2 file. Please note, don't save it as an XYZ file because you will miss the bond interaction. So save this. So save it as a mol2 file. So this is good. So once you've saved it here, you can close this. Now the next thing you want to do is to optimize the structure. You want to optimize the structure. And how do you do that? Using Gaussian. So I'll close this and then I'll open GaussView. So open GaussView. And then the next thing you want to do is to import the structure. So go to open and then you can navigate to downloads, then talking metal complexes. You can see there's copper, you can see this. So open it. Good. Now so you can see the structure. Now what you want to do is to just optimize the structure using um just molecular mechanics or semi-empirical methods. I would prefer semi-empirical method. So go to Gaussian calculation setup, and then we just want to optimize. So click on optimization, and we don't want to use Hartree fork. I'd prefer to use semi-empirical, and I will use PM6. The charge is actually 0, and then I will leave everything the way it is. And then this, okay. Then you can preview, and then we can submit. Now to submit, we'll have to save. So I'll save this as, yes, I'll save it as this. So let's save, and then yes. Now you can see that our structure is being optimized. You can see that. So we would wait for the structure to get fully optimized. So you can see that the optimization process is complete. Gaussian says Gaussian job has completed. Do you want to close the Gaussian window? Then we can click on yes. Now the next thing is to open this. This is our output file, so we're going to open it. So go to open. Yes, I can see it. Okay, wow. So this is it. You can see it. So what we'll do is to save this file. So click on file and click on save. Now we're going to save it as a mol2 file. So I like to save it as this, and I'll put optimized. So and then we can save it. So this is good. So we can now go to that directory to look for it. So you can see it here. So this is the optimized file. Now once you're done optimizing your complex using the parameters, the next thing is to carry out molecular docking using MOE. So I'll open that. Okay, I think I have it here. So we can cancel this. We can close this, and then simply go to MOE. Okay, so The first thing you want to do is to import the files you have. So let's go to file, go to open, and let's navigate to that directory. So it's in downloads. So we're going to be importing the um, protein and optimized file. So we have this, and then so apply. Okay, so this is good. Now we can see this is our protein. Look at it. So this is our protein. Now let's work on it. Now the first thing we want to do is to remove all of the water molecules. So right click and delete. Okay, so same here. Delete the water molecules. Now we'll also delete this magnesium and co-crystallized ligand that comes with the protein. So I'll delete them. Okay, good. So the only thing I have there is the A and B chains of 1IR3, and then I can leave it that way. And we can also see our ligand. Let's look at ligand and let's see if it's there. Oh, beautiful. So you can see, look at the ligand. We've imported it. So this is the structure of our ligand. Now, in this case, this is our metal complex. So I've imported the metal complex. So we can close this. Let's close this. Now, the next thing you want to do is to minimize your structure. So let's see if we can minimize our protein. So what we just want to minimize is this, and then so okay, so let's minimize it. Now it's a choice to minimize or not. Yes, it's a choice. You have to choose. If you don't intend to minimize, then it's also fine, depending on the kind of system. Sometimes excessive um, minimization can affect the binding pocket. So let's just minimize, but it's a choice. You can choose not to minimize. So once you start to minimize, it tells you what is going on. Now the next thing we want to do while the minimization process is taking place is to um, okay, we can also find the site, but let me allow it to minimize, and then we can find the site. Now the minimization process for the protein is completed. So the next thing we have to do is to go to site finder. So before we do that, let's do something else. Let's do a quick preparation of our protein structure. So just click on OK. Yes. So we always try to prepare our protein before carrying out the docking process, and you can just simply use that quick preparation to prepare, and then it completes. So the preparation has taken place, it's complete. So what we need to do is to go to compute. The first thing you need to find is the docking site. So let's go to site finder, click on it, and then here isn't this now. What you do is simply click on apply. Now it will give you different sites, so we're going to be using the first one. So click on it and then select contact atoms, and then you can apply. Once you've done that, you can close this. You can close this. Now the next thing to do is to actually dock. So I'll be docking. Click on dock. Okay, so I'll be using this. This is my receptor. Um, for my site, I will use selected atoms. So click on this selected atoms. Remember, we chose the active site and then we activated the selected atoms. So we are choosing selected atoms. Then for ligand atoms, since in fact we have the structure here, this is what we'll be using. So these are structure. You can also choose to load your structure using this, but we'll be using um, the molecular operating environment system submission, and that's the structure. So for time's sake, I will just reduce this to 2. I'll reduce this to 2. Now you can also choose different scoring functions. So whatever scoring function you want to choose is fine. You can choose to change the scoring function. Now what we now need to do is to simply run. No. So let's cancel something. Now here in our output, let me change something. So we want our output to be here. So our output, we want it to be um copper complex. Okay, copper complex docking output. You can choose to save it, so I'll just save it that way. Okay, dot mdb. Okay, so that's fine. Now the next thing we have to do is just click on run. Now once it shows you this, it means the docking process has started. So when it's complete, it will notify us. Now the docking is complete. You can see that. So you can see the two results. So minus 5.1598 minus 2.826. So these are the results of your docking. Remember, we docked using the triangle matcher and rigid receptor, and then so we had two results. Now the interesting thing about molecular operating environment is that it saves this result. So imagine that you want to visualize this result. Just click on this. So I can close this. Wow. So I can click on it and then it tells me clear system before loading data. So I want to do something. I want, okay, I think I want to, okay, that's it. Okay, cool. So now, so no, I don't want it to clear the system before loading data. Now, so once I clicked on that, it eventually brought the um, complex that we docked into the active site. Now to see that, simply just click on I think show ligand interactions. Oh wow, this nice. So you can see, now look at our complex and look at the interactions. The interactions between the complex and different amino acids with tyrosine, aspartate, and many others. So you can see. Now you can choose to export this using this. You can choose to export it. You can also choose to. Okay, so let's export it and let's navigate to that folder. That will be under download. So let's call it interaction. The PNG, and then we can export it. Also, you can see that. So you can choose to export this. Now, beyond this, you can also choose to see the interactions. Okay. Oh, so it's giving me the same thing. Now you can see the structure of our protein, and then you can see the metal complex within its cavity. So I can choose to render this differently. So click on this, and then you can see that. You can also choose to render it using bolts. But let's leave it like this. Now, so this is it. Now, if you want to once more, if you want to visualize the interaction, just simply go to ligand interactions, and that will give you what you are looking for, and then you can use it, and then you can use it for your publications, your papers. Now, and it's very clear and very easy to relate with. The different colors will tell you the different kind of interactions that you find. Now, you've learned how to carry out molecular docking using molecular operating environment, and then in conjunction with Gaussian and Mercury. And we also, don't forget, this is for structures that were downloaded from a chemical database. So I know you've learned a lot. Thank you for listening. Now, just to provide some important information. Now, this is um, the paper that gave us the CCDC number we used. So I want to reference this. Now, thank you for listening. Have a nice time. I want to also hear from you. Bye bye.